Hello everyone, I am Micah Corah. Today I will be presenting my paper, Volumetric Objectives for Multi-Robot Exploration of Three-Dimensional Environments. This was part of my thesis work at CMU, advised by Professor Nathan Michael. Presently, I'm a postdoc working at the NASA Jet Propulsion Laboratory. So why should we care about robotic exploration? One application that I'm interested in is urban search and rescue. In this domain, robots can provide valuable situational awareness to first responders, as I have illustrated in this cartoon, such as by providing maps of the environment, assessing hazards, and locating survivors. Subterranean search and rescue is also the subject of the DARPA Subterranean Challenge, and I am currently competing in the competition with Team CoStar at JPL. In this talk, I will focus on teams of robots mapping the geometry of free and occupied space in unknown three-dimensional environments using onboard LiDAR or depth cameras. And when I talk about exploration with volumetric objectives, what I mean is that robots can explore complex environments quickly by maximizing the amount of unknown or unobserved space covered by future observations, say over a horizon of several seconds. Here, we see a robot observing some of the unknown space, which may turn out to be free or occupied, which is shown in gray. By maximizing the amount of unknown space the robot will observe, we can obtain interesting and dynamic maneuvers, and this is something that I find quite exciting. So here we see a robot executing a sort of spiraling motion to quickly and safely cover the unknown space, and we obtain this by optimizing trajectories to maximize a volumetric objective. In this presentation, I will present expected weighted coverage as a general volumetric objective for robotic exploration, and I will apply expected coverage to unify certain information-theoretic and coverage-based objectives. Specifically, I will look at mutual information without noise. I will then go on to present a few applications and experiments. First, expected coverage will prove to be a useful tool to enable distributed planning for multi-robot exploration. Then, I will discuss some insights into objective design obtained via interpreting objectives in terms of expected weighted coverage, as well as a brief comparison of existing coverage and information-based methods. For context, recent works on exploration apply a variety of different objectives that each capture the value of observations of unknown space from a given camera view in slightly different ways. Coverage-like objectives emphasize the part of the environment covered by an observation. In general, coverage objectives are simple, practical, and easy to implement, and later we will also show that coverage objectives perform well in practice. Mutual information objectives for mapping with depth cameras seek to model reduction in uncertainty in the map explicitly, and information-based methods have been the subject of numerous recent works focusing on topics such as analysis and algorithm design. In the following slides, I will draw a number of connections between these two classes of methods in terms of expected coverage. Additionally, I will present what I believe are the first published results comparing coverage and information methods. One example of a coverage objective, one of the simplest and most common, is what I like to call optimistic volumetric coverage. With optimistic coverage, robots are rewarded according to the volume of unknown space covered by their hypothetical future observations, assuming optimistically that all of the unknown space is empty, which provides the maximum possible reward for a set of camera views. Changing tracks to information-based objectives, many information-theoretic objectives are based on some form of mutual information. Mutual information characterizes how much information observation of one random variable will provide about another. As written here, the mutual information provides the expected reduction in uncertainty in the map X after obtaining the robot's observations y1 to yn. What is great about information-theoretic objectives is that we are often able to evaluate mutual information for individual range observations in closed form. Specifically, we can do so for discretized environments with independent occupancy probabilities, like occupancy grids or as in octamaps, and with additive noise, typically Gaussian. However, we generally have to approximate mutual information for observations involving multiple rays or camera views. One way to do so is to compute a sum of exact values for nearly independent rays, like so. While summing rays as such is a useful approach, approximating independence leads to some difficult trade-offs, and it is unclear how accurately this and other methods are able to approximate mutual information for multiple views, either along a trajectory or for observations by teams of robots. Going into a little more depth and regarding noise in range observations, recent work by Jung et al. Compared different information-theoretic methods and noise models and did not encounter a significant impact on exploration performance. This led Henderson to develop a method for evaluating mutual information that assumes little noise, and that small noise assumption can be justified given that the noise in range observations, typically on the order of centimeters, is often small compared to the scale of the discretization and the maximum range of the sensor. I will also add that Henderson's work solves some challenges for evaluating one or more camera views, but we'll not have time to go into more depth on that subject in this talk. This leads us to the model of mutual information we study in this work. Like prior works on this subject, we assume a discretized environment with independent probabilities of cell occupancy. And following the line of Henderson's work, we will assume noiseless observations of the distance to the nearest occupied cell. Now we can characterize both coverage and information-based objectives in terms of expected weighted coverage. Here, consider the volume of unknown space a robot observes from a given camera view and for distribution over different possible realizations of the environment in the unknown space, like so. More generally, we can define a set of non-negative weights which represent rewards for observing each cell in the environment. And the expected weighted coverage objective is the expected weight of cells observed for a collection of camera views, as shown here. An exciting result from this work is that mutual information without noise fits the form of expected coverage. In other words, this special case of mutual information is a kind of coverage objective, and this can both simplify analysis and lead to efficient and accurate algorithms for evaluating mutual information. We demonstrate that mutual information without noise is an expected coverage objective by writing the mutual information in the form of expected coverage, as shown here. Although the proof is simple, please refer to the paper for more detail. Now, let us begin to apply this result. Interpretation as expected coverage can be used to prove functional properties of mutual information and other objectives relevant to distributed perception planning for multi-robot teams. Specifically, we present results and analysis for a method of distributed submodular maximization developed as a part of my thesis work. More broadly, the framework of expected coverage can be used to model a variety of objectives for volumetric exploration and active perception tasks. To begin, the optimistic coverage objective I described earlier can also be written as an expected coverage objective by assuming unknown space is empty with probability 1. Likewise, optimistic coverage is equivalent to mutual information without noise when the prior probability of occupancy for unknown cells is small. And additionally, the mutual information can be approximated by obtaining trivial upper or lower bounds on the probabilities of observing each cell in the discretization. Now, I would like to present some initial results comparing information and coverage-based methods. Here, we compare the optimistic coverage objective I have been talking about to CSQMI, an information-based method, for 10 trials with a team of robots exploring the boxy environment on the right. And we found that the optimistic coverage objective provided a 16% improvement in completion time in these experiments. Although this result may go against intuition, as information-based methods are generally posed as being more advanced, the approximations I highlighted earlier are a potential cause for the difference in performance. To conclude, In this talk, I have presented expected weighted coverage as a framework for studying volumetric exploration objectives. Our contributions regarding expected coverage are notable for enabling distributed multi-robot planning for exploration, as well as unifying coverage and information methods, and leading to various insights regarding objective design. Now, I would also like to highlight some of the next steps for future work. First, the experimental comparison of coverage and information methods was limited in scope, and more in-depth comparison is warranted. Likewise, I briefly mentioned how expected coverage can be applied to develop algorithms that efficiently approximate mutual information, and implementing and evaluating such approaches is an important direction for future work. Finally, I hope that this work spurs the development of more nuanced exploration objectives, as well as more detailed evaluation of existing approaches. Thank you for listening. I am Micah Corah, and this concludes my talk.